Okay, so, come on, computer. There we go. Okay, so this was where we were at. We had figured out the maximum acceleration. So I guess before I go anywhere, is everybody okay with how we arrived at the result? That the maximum acceleration that he could give the peanuts and the kittens was 3.92. Okay, we figured out that the maximum friction between the kittens and the peanuts was 156. That's the force that's going to push the kittens forward, right? And so, since the maximum force pushing the kittens forward is 156, the maximum acceleration is dependent on that net force. Good? Maggie, you good? Whatever. Don't whatever. If you're confused, ask.
I asked if you could just say that was the acceleration of the entire system. You said that would be right. So I just plugged the acceleration back in to the I plugged the force back into the peanut
Which force? The 156?
Yes.
Okay.
And I found the acceleration of that. I found the force of Roy for that. And then using that, I found the acceleration of the system. And then it said,
Okay. I don't know. I don't remember you asking me that. They should have the same acceleration. So either you misunderstood me or I misunderstood you or something. I'm not sure what happened there. I don't remember that conversation now. But yeah, I mean, the goal was, if I remember right, the question says, what's the maximum acceleration you could give the crates without the kittens slipping? So the goal is we want them to move together.
okay.
So they should have the same acceleration. And if I said something that led you to believe that was not right, I apologize. Okay, so, yeah, Adam?
But wouldn't the acceleration be different because you're adding both masses, not just the mass of the kittens?
I agree that the acceleration of the system depends on the whole mass. Yes. So certainly the crate is going to, the system is going to move slower than it would if the kittens weren't there because you're pushing more mass. Is that what you're saying?
No, I'm saying it would move faster if the peanuts weren't there.
Right, yes. I agree with that.
And I don't know, I'm just...
Do we need to go back and rewind and go through part A again?
Yeah.
Yes? Okay. All right, so let's start from scratch, which is okay. That's all right. Okay, so I guess my recommendation, you guys, is when you solve these problems, you're going to end up having to make sort of 3 free-body diagrams.
Are you recording?
Okay, yes, I am. Thank you. You're going to need to make 3 free-body diagrams. All right, you're going to have to make a free-body diagram for the combined system of all of your objects, and then one for each of the individual objects. Follow? All right, so let's take a second and draw those 3 free-body diagrams without any numbers. Okay? So, it doesn't matter the sequence you do it in. Let's start with peanuts and kittens. So here's the peanuts plus kittens system. All right? So that had a combined mass of what, 160 kilograms, right? Okay? So what forces are going to act on this? You guys help out. Just shout them out. What do we got? Force of gravity. Normal force. Force of Roy. Friction. Let's see. Is there any friction? Let's see. Yeah, I think we had decided that the floor was frictionless. Okay. So the only friction here is going to be between the peanuts and the kittens. Do I need to draw that here? No. Why not? What's the name of that kind of force, guys? Internal. It's an internal force. All right. So remember, you guys, and this is important, when you make these free body diagrams, the only forces that go on your drawings are external forces. So you only need to draw forces that come from outside of the system. Cool? All right, so are there any other forces?
No.
No. Okay. So from this point forward, when I write with red, that will represent what's going on with the system. Okay? All right, now, let's look at, I don't know, you want to do the kittens let's do the kittens first because I think it'll help us understand the peanuts a little better. All right, so let's do the kittens. So here's the kittens. They have a mass of 40 kilograms. Okay, so our forces are gravity, And normal force, we should be specific here. Where's this normal force coming from, you guys?
Peanuts.
From the peanuts, right? The peanuts are holding up the kittens, right? Okay. So I don't know that that's super important in this point. At this point, I guess I do want to specify something about it. So let's call this the force on the kittens by the peanuts, right? All right. All right. So that's that, right? Now, horizontally, are there any other forces? Friction, right? So here's my peanuts. Here's my kittens. Right? Roy is pushing the peanuts, and the kittens move too, right? Do you guys understand that it's friction causing the kittens to move forward? What kind of friction? Static. All right? And since we're trying to find the maximum acceleration, my board needs to be calibrated. Since we're trying to find the maximum acceleration, I want to find the maximum force, right? Because if I maximize that force, I maximize the acceleration produced. Everybody good up to there?
Yep.
Any problems? Okay. Now, this, we should be maybe a little more specific about it. Where does that maximum static friction come from? Like, it's the friction between what and what? The peanuts and the kittens again, right? So this is another force on the kittens by the peanuts, isn't it? So there are two forces on the kittens by the peanuts. They're providing a normal force to hold up the kittens, and they're providing friction to push the kittens forward. Follow? So you might want to do one of these, call this the y component, and call this the x component. All right, any problems with that? I'm getting a lot of blank stares or no stares. Sarah, talk to me, what do you got?
Wait, so what's the up friction again?
Say that again.
What's the friction up again? Sorry.
It's not friction up. It's so as he pulls or pushes the kittens, the peanuts are holding them up, right?
Okay.
So this upward force, this y component, is a normal force. It's not friction.
Oh.
Is that a genuine O or is that a?
Yeah.
Okay. Yeah.
So for the static friction here, is that going to be calculated by the normal force that we have right there?
Correct. Yeah. All right. So is everybody good up to there?
Yeah.
Yep.
All right. So last thing we got to do is make a drawing for the peanuts. I don't know where I want to draw this. I wish I had more room. All right, so here's the peanuts. Our mass is 120 kilograms. So once again, gravity is going to pull the peanuts down. All right. Now, be careful here. There are a bunch of forces on the peanuts. So what else? You're pointing down, Evan. Give me 2 seconds. Why are you pointing down? Good. Look, this is why I wanted to make a point of this. What's holding the kittens up? The peanuts. So, peanuts push kittens up. That means kittens push peanuts down. So there's a downward force on the peanuts from the kittens, right? So let's put a little y there to indicate that it's downward. Carly, you said you had a question.
Yeah, that was kind of actually my question. I was going to say, is that like the force of gravity from like the kittens being on there? Okay,
Yeah.
then that was my question.
Yeah. In this one, yes. It won't always be, but yes. In this one, the gravity's pulling the kittens down, and as a result, they're pushing down on the surface there. Yeah.
Is there ever going to be a problem where that force is going to be like necessary?
Yeah, sometimes.
Okay.
I think rarely, but it does come up.
Oh, when there's going to be friction.
If there was friction here, this would affect my normal
Yeah.
force, right? Does that make sense, you guys? So if there was friction between the peanuts and the floor, then that would affect my normal force, right?
Yeah.
All right.
Then wouldn't that
And so it gets ugly. Wouldn't that what?
like affect?
And that would affect the system, and yeah, it gets ugly. I know.
Okay.
All right, so are we good up to here? All right. Oh, I drew in the normal force. Where's that normal force coming from? From the ground, right? Okay. All right, 2 more forces. What do we got?
With the top.
Roy. Let's do Roy first, because that's the easy one. So there's the force of Roy pushing the peanuts. And there's one other force. force of friction, right? Okay, the idea is because of friction, the peanuts are pushing the kittens forward, right? Well, as a reaction, that means that the kittens are pushing the peanuts backwards, right? Oh,
Okay,
darn
that's
it.
the part that I don't really understand.
That's the part you don't understand. Okay, so let me. Nope, that's not what I wanted to do. All right, so here, let me try to explain this a couple different ways. All right, so the first way is kind of the textbook explanation. Okay? So Sebo, describe for me, in terms of one object pushing or pulling another object, describe for me the static friction on the kittens.
Not gonna move,
We're not going to slide.
because the boxes are like that. Is that right?
Yes.
So one
So-
trying to go that way, but friction would be like, no. Oh
Yes.
wait, no, but here's what I don't understand. If it's moving this way, why is friction not going this way?
It's going to be. On the peanuts, you mean?
Stalking kittens.
Are you talking peanuts or kittens?
Kittens.
Let's get on the same page.
Kittens.
Okay, so here. Remember I did the...
Yeah,
shoot.
yeah.
So look, if there's no friction... Is this level enough? Darn it. If there's no friction,
Right.
so point for me. Relative to the table, which way did the cart just slide?
Left.
Right? Relative to the table, the cart slid to the left, right? So to prevent it from sliding to the left, which way do you have to push it?
Right.
To the right.
Okay.
Follow?
Yeah.
Everybody good?
Yep.
All right, so once again, describe for me, in terms of one object pushing another one, this force of friction.
Okay. Friction is gonna push the kittens to the right.
Okay, so that's one object, kittens. What's the other object? Friction's not an object.
Oh, the force of the peanuts on the kitten is gonna push to the right.
Good.
Okay.
Yep. So this is the static friction between the peanuts and the kittens, right? That static friction is going to move the kittens, so that force must be coming from the peanuts. So this is the force on the kittens from the peanuts. Good? So the crappy textbook explanation of what you're confused about is, so if the action is peanuts push kittens, then what's the reaction? Kittens push peanuts. So that's going to be over here. There's going to be a backwards force from on the peanuts from the kittens. Good? Equal to this. All right? Now, here's the conceptual explanation.
Good thing I wasn't sitting there.
Uh-huh. All right, look. I'm going to push this thing this way with 100 newtons. Moves, right?
Yeah.
Agreed?
Yeah.
Versus. Now I'm going to push it this way with 100 newtons again. Did it move as fast? All right.
Sit down, I'm distracted.
So pretend it didn't fall. Should it have moved as fast? No, because I'm moving more mass, right? Okay? So technically what happened there is I was pushing the desk forward. The desk pushed the chair forward. Pretend it didn't fall. And so the idea is because the desk was pushing the chair forward, the chair was resisting the forward motion of the desk, thus slowing it down. Okay, so that's the sort of non-textbooky, concept-y explanation. Okay, so what I just did there, I wish it hadn't fallen off, but so this, you guys, you guys agree that the chair is slowing the desk down?
Yeah.
Okay, putting it on top is the same thing, right? Okay, except now instead of it being a contact force, it's friction force, which I guess is still technically a contact force, but good?
Yeah.
All right, so are we good? Something that I found helpful as I was writing up my answers to these problems, you guys?
Hi.
bless it. That's going to fall, so look out. Don't die. All right. Something that I found helpful as I was doing this, you guys, is I went through and I highlighted. Literally, I grabbed a highlighter out of my notes. Really and truly, I'm going to show you. Do you see all the pretty colors on my notes?
Very pretty.
Very pretty. You know what I did? I highlighted action and reaction forces. So, if this is my action, what's the corresponding reaction? This guy, right? Why would that maybe be helpful? Because not maybe they're equal, definitely they're equal.
I know, I was just
Right?
form.
Okay? And is there another action-reaction pair here? Let's see. You guys are talking about gravity.
Gravity of kittens.
So gravity of kittens would be Earth pulling kittens down. What's the reaction to that? Kittens pulling Earth up. We don't care about that.
FPKY.
Okay. So that's the force of the kittens pushing the... No, the force of the peanuts pushing the kittens up. And that's the force of the kittens pushing the peanuts down. It is insane. It's a lot to... I know, I get it.
Should we not call that gravity?
Correct. You should not call that gravity. Because
Okay.
it's not. Because when you talk about gravity, you're talking about the Earth pulling something down.
Okay, I thought, okay, that's
It happens in this problem that it's equal to gravity.
alright.
Do you know what I mean?
Yeah.
But it's not technically the same force. Okay. Are we good? Once you've done a few of these, I don't mind taking a long time on this example because I think once you kind of figure these out, you'll see they're the same strategies over and over. Right? And then the process is just, here's another example of the same thing, different configuration, but same ideas. Yeah.
What you just did, can you not highlight the green FG with the pink?
No, because this and this, that is not an action-reaction force, or action-reaction pair. So remember, action-reaction pair, and you guys all need to hear this. At any time, so these, I agree, these two forces are equal and opposite.
Okay.
Carla just asked if you could highlight those, if that's an action-reaction pair. Okay? Specifically,
I get
this.
why they're not action-reaction. I was just thinking we were finding things that were equal so that I
I see. Okay, I see. So does everybody understand that those two that I just put crappy blue stars next to are not action-reaction pair?
Yes.
Right? Because to be action-reaction pair, it's got to be of the form A pushes B, B pushes A. Two objects, right? And that's not what this is. This is with peanuts push kittens, and this is Earth pulls kittens. So not action-reaction. Zach.
Okay, I was going to ask if acceleration needed to happen, but I just realized it doesn't.
All right. Okay, so we've kind of dissected this with just letters. We haven't put any numbers in. I'm sticking with the word putting. We haven't put any numbers in yet. All right? Are there any problems with what we've done? All right, so now let's put in some numbers. All right? I'm going to do this kind of quick here. So our force of gravity on this is, what's 16 times 9.8? 15. How about if I look at my notes that are all highlighted and pretty?
Is that the 156 or no?
Wait a minute.
Why do you actually...
1568. Okay, so everybody good with that? And so our normal force is also going to be 1568, right?
Yeah, it's 156.8, right?
Uh-uh.
16 times 10.
It's not 16, it's 160.
No. I guess we all made that error then.
Right? Isn't it 40 kilograms and...
Yep. Yep.
Are we good or no?
We're solid. It's just on the notes yesterday we all multiplied it by 16.
Oh, really?
Yeah. Yeah.
Yeah, and I got that.
The 156.8 weirdly comes up somewhere else.
Yeah, it's the...
Oh, that's the.
That's the x component of
Yes, yes.
friction. All right, so is everybody good with what I drew here in red?
Yeah.
Do we know the force of Roy?
Maybe we do.
We do not yet know the force of Roy. Okay? All right, now, so since I don't know the force of Roy, I don't know the force of Roy here in my blue drawing either. So let's look at the green drawing. Good? All right, so let's do this. I got to calibrate my board real quick. Sorry.
Do you know why highlighters are prohibited on AP tests, Mr. Eckert?
I do not. Oh my gosh.
Why would that be easy?
Okay. Oh, that could be because people next to you could see. All right. Okay, so let's do this, you guys. So, all right, you guys said you wanted me to go back and go through this, so follow along. All right, so this force of gravity here is negative 392. This normal force is 392. Is everybody cool with that? All right, so now I can find my maximum force of friction by doing coefficient times normal force. And by weird coincidence, that gives you 156.8 newtons. I apologize for the similarity between that and our force of gravity.
So then, is that the same as the other green?
So that means that this is also going to be 156.8. So let's go ahead and put it in.
And the pink is 392.
Good? All right, so let's finish up with this green drawing. Are there any other forces in the green drawing? No. So I can find my net force and acceleration, right? Okay? Maximum acceleration is achieved by maximum force. So acceleration is net force over mass, and it gave you the 3.92 that we got yesterday. Better? Everybody good?
Yeah.
Thank you for asking questions. Like, there's no point in us moving on to harder problems if you guys don't get these. So, yeah.
I just still don't understand, because if you're pushing the whole system, you're pushing a mass of 160 and not a mass of 40.
I have not said that I'm pushing a mass of 40. That wasn't meant to sound snarky.
I know.
What's pushing the 40?
What's pushing the 40 with peanuts?
Right.
Yeah.
So let me finish, and then I think you'll see how stuff works.
Okay.
Okay? All right, so is everybody good with the green?
Yes.
Okay. I'm going to erase just where I found the acceleration, just to buy a little room. Is that cool?
Yeah.
All right, now. All right, so Adam, I guess I'll let you pick. Are you confused about the green drawing, the red drawing, the blue drawing, or all of it?
It's more like just conceptual, like, can I
Okay.
try something? Can I get up and do something with the chair?
Sure. Yes. Come on up.
With the chair.
Oh, with the chair?
The chair.
Oh my gosh.
Oh, watch out.
All right, let me get something that's not a chair. Won't kill anybody.
Oh, here. I can try that.
Got a textbook.
Can I do this? Can I do this?
Yeah.
So, like,
Okay, shh, guys, quiet, please, so I can hear and so you can hear.
so,
All right, so Adam's got the duck on the skateboard.
so if this is the mass of 40 and the skateboard is the mass of 120, and the force of friction is 168, was
Yeah,
that what it was?
156. Sorry, here, I'll go back.
So if you push the skateboard with 168 newtons, it shouldn't slide.
Are you talking the 156? Is that what you're talking about?
Oh yeah, 156, yeah. That's
Okay.
what I meant.
There's no.
We haven't looked at the skateboard yet. In your example, all we've looked at is the duck.
So you're trying to find the acceleration of the duck as if the skateboard wasn't there. There's, if, like,
From your perspective.
Let me finish. I think once I'm done, I think things will call together.
okay.
There's also no friction.
All right, you guys. So look, so Adam, to answer your question, let's now focus on the skateboard. Let's focus on the peanuts. Okay. So, let me do this. Peanuts. Good? All right, so what do we know about the peanuts? Well, we just found their acceleration, right? Because what we've decided is that the maximum acceleration we can give the kittens is 3.92. Okay? And since the goal is to have them not slide, that means that the peanuts underneath them also need to be moving at 3.92.
Yes.
You good up to there, Adam?
Yeah.
Is everybody good up to there? All right, so the acceleration of our peanuts is 3.92 meters a second squared. Everybody in the room, what should I do now? I just wrote down an acceleration. What should I do? Find the net force. Okay, so the net force on my peanuts is the mass of the peanuts times the acceleration of the peanuts. Bear with me.
Yeah.
So, mass of the peanuts is 120 kilograms. That's just the peanuts. Okay? And they're accelerating at 3.92 meters a second squared. So that means that the net force on the peanuts turns out to be... a number that I don't remember off the top of my head, and it's apparently not written on my crappy notes.
Pretty close to 400.
I know, but we need to know exactly what it is, and I don't have a calculator. What do you got? 470 who? Point what? Oh, 470.4. I do have it written down. Sorry. There it is. Okay. Are we good? All right. Now, so if that's the net force on the peanuts, let's now think about the forces over here that are affecting the motion. Well, the kittens are pushing back on the peanuts, right? Because when we push the peanuts, we're not just moving the peanuts, we're also pushing the kittens. So the kittens provide this resistive force against the motion, because they have inertia. Okay? So that 156 newtons represents the backwards force on the peanuts. So to get this acceleration, we're going to do net force equals net force. 470.4 equals the force of Roy plus the force on the peanuts from the kittens. Okay, and so what I'm trying to show you here is Roy actually has to push harder than he would if the kittens weren't there, because the kittens are pushing back, which I think is what was messing you up a little bit, right? Yep. So Roy, in order to get this acceleration, if the kittens weren't there, then 470 newtons would do it, right? If the kittens weren't there, then he could just push forward with 470 newtons and we'd be good. But because the kittens are there, he's got to push with an extra 156 newtons to move them also. Do you see what I'm saying? So when you add the 156 to both sides, the force of Roy turns out to be 627.2. Good? Everybody good?
Yes.
All right, so now I can put that on this drawing. Good? Any questions?
No.
Adam, are you good? Do you see what I'm saying? Does that clarify a little or no?
It makes it better.
Better at least? Okay. All right, and then finally, if we put the 627 up here, then that drawing is done. And if you divide by 160, what acceleration do we get? 3.92 again. Right? Because this represents the whole system. Good? I'm getting... Some people are totally zoned out. Some people are looking super confused. You guys got to help me. Where are we at?
We're good.
Are we okay? Okay. Carla? All right. Cool. Lot to keep track of. Okay? Yeah, Cam.
So wait, that force I just found is a maximum force that Roy can use, like, for...
I'm so glad you're about to say this. Sorry, I interrupted you.
No, you're good. So like, that's the maximum force Roy can use that, the kittens will stay on top of it.
Yes. So what this 627 newtons represents, thank you for saying this, I was going to wrap it all up with this, and you anticipated what I was going to say next. This 627 newtons is the force that makes the peanuts and the kittens slide at 3.92 meters a second squared. What if he pushes with more force? Then they slide, right? Because he'd be producing too much acceleration. Okay? Carla?
So the mass and since the mass is bigger and the acceleration is the same, and the net force has to be like smaller.
Hold on, rewind. Say that again. Since the
mass is bigger
on the red drawing?
Yeah, and the acceleration is the same, then the net force is going to have to be smaller. And is that because
Wait, what net force is going to have to be smaller?
on the system is going to have to be smaller than like the others compared because it has a bigger mass but the same acceleration, so it has to like counter it?
If you've got a bigger mass, then to get the same acceleration, you'd have to have a bigger net
Oh,
force.
yeah, okay. Okay,
Right? Good?
Yep.
Is that, you good?
yeah.
Zeke?
So, until we reach the condition of like acceleration equaling whatever it is, like 3.92 or something, you can treat everything like as though it's under a blanket, like you can treat it as though the kittens are glued to the peanuts.
Sure.
Almost.
Yeah.
Okay.
And that's what this red drawing is doing.
Okay.
Right? Because they're moving together.
Yeah.
All right.
Alright,
Follow?
yes.
All right. So here's the deal, you guys. Let me summarize. I know a lot of you guys are like, The process always works the same. You're always going to have free body diagrams. One for each of the individual objects. Well, one for object A, one for object B. So that's 2. And then one for the combined A and B together. Okay? How do you know which one to start with? Depends on what you know. Okay? So my recommendation is if there's one of those free body diagrams where you know all the forces, great. Start with that one. Okay? If you know the acceleration, then find all of your net forces. Okay? All right. So, how are we doing? Is there anything else I can clarify before we try part B?
You're set.
Okay. All right, so here's the deal with B and C. And you guys can tell me if this is going to be valuable to do this.
Both of them are just static.
Let's just do one of them. Like,
Yeah.
wait, first you can explain it, and then I don't even think we'll need it, but maybe.
Okay. So 2, it says, all right, so what we just discovered is if we push with 627, they both move, right?
Yeah.
And they move together. Okay? So 2 says, what if we only push with 480? Okay, so basically what happens is, if this force is 480, they'll move together, right? So you get a smaller acceleration. I think it turns out to be 3.
Yep.
Okay? And so what that means is static friction doesn't need as much force to prevent the sliding. And so your force of static friction ends up being smaller than the max. I think it turns out to be 120. So that's number 2. Good?
Yeah.
All right, so why don't we do number 3? Because number 3 has something sort of weird happen. Okay? Yeah, Cam?
So when you're asking this, like, what are you?
I know. So in the notes, the questions are real open-ended.
Yeah.
On a homework assignment, problem 2 would have said, if you push with 480 newtons, find the acceleration of the system and make a free body diagram for each of the individual objects. Or something like that.
I just want to know.
Okay, I know, and I realized that. A couple of people said that, which is why I ended up abandoning my homework check. All right, so are we good? All right, let's do number 3. So number 3, I sent out a remind where I asked you to increase the 600 to 800 newtons, right?
Oh.
Okay, so if you didn't do that, scribble out the 600 and write in 800. All right, so Hunter just said that changes the problem, and it totally changes the problem in a really big way. So everybody pause for a minute. Why does making Roy's force 800 newtons create a significant change in the problem? I want everybody to think for a minute before I call on anybody. Okay, sure, what do you got there? Good, the kittens are going to fall off. They're going to slide across the top of the peanuts. I keep wanting to say puppies. So this time, the 2 objects are going to have different accelerations, right? What's going to accelerate faster, the peanuts or the kittens?
The kittens, yeah. Right? No? I thought it was kittens. Peanuts. The kittens
Here.
are still moving.
If they slide off, if the kittens slide off, what accelerates more, the peanuts or the kittens?
Peanuts.
The peanuts, right? Because the kittens are, in this case, not accelerating at all. In our case, they're going to accelerate forward, but not enough to prevent them from sliding off. Follow?
Yep.
Okay, so let's try it. Okay, so here we go. So in this one, this is important, you guys. guys, this idea here is important, so you're probably going to want to write this down for that third part of this example. All right? Because the force of Roy equals 800 newtons means the kittens are going to slide. The kittens and the peanuts don't move together. So I'm going to say loosely, can't treat them as a system. There is a way to do it, and we'll deal with that in a couple chapters, but for now, we're not going to worry about it. Does that make sense? Because they're going to have different accelerations, right? So it wouldn't make sense to talk about the acceleration of the peanuts and the kittens because they're moving at different rates. Follow?
Yes.
Okay, so let's make two Freebody diagrams. One for the peanuts, one for the kittens. What color was I doing? Peanuts in. Peanuts were blue, kittens were green. All right, so here we go. Kittens. 40 kilograms, right? So, force of gravity, negative 392 newtons, right? Normal force, which is actually the force on the, which is actually the force on the peanuts from the kittens, is positive 392 newtons, right?
Force on the kids.
Oh, yeah, I have it backwards, don't I? Thank you. Ugh, stupid notation. On the kittens from the peanuts in the y direction.
Economics, I thought P was for potatoes.
All right. Everybody good? All right. Now, are there any other forces on the kittens?
Yeah, kinetic.
Kinetic friction, right?
Yeah.
Okay. So the idea is the kittens want to stay at rest relative to the peanuts, but there's a little bit of friction, right? The molecules from the peanuts moving underneath are going to grip the kittens and push them which way? Forward, right? Just not fast enough. So here is the force on the kittens from the peanuts in the x direction. It's equal to the force of friction kinetic, which is our coefficient of kinetic friction times our normal force. So that's, what was our coefficient of friction again? 0.3. So 0.3 times 392 gives you a number that is written on this highlighted piece of paper, 117.6.
Yeah.
Make sense?
Basically, when you did the chair thing, you thought it was going to be static, and
And then it was kinetic, exactly. And that was why I was screwed. All right, everybody good?
Yeah.
All right, are there any other forces on my kittens? I think that's it, isn't it?
Yep.
So we can find our acceleration. Acceleration of the kittens is the net force on the kittens divided by the mass of the kittens. What's my net force?
117.
The gravity and normal force cancel, so you're just left with the 117. The mass is 40 kilograms. Divide it out, and you get 2.94 meters a second squared. Follow? All right, now let's look at the peanuts. Peanuts, 120 kilograms. So we got gravity, which is negative 1176. What else? Kittens pushing down with how much force? 392, right? Oh no. So that's the force on the peanuts by the kittens in the y direction, right? What else, you guys? Two other forces. No, three other forces.
Normal force.
Normal force.
15.6.
They're not going to go down through the floor. So that's got to be 1568. Which, well, never mind, I won't go there. Okay, good. You got Roy. How much? 800 newtons. And
The kittens.
friction, right? So the peanuts are pushing the kittens forward. That means
Kittens are pushing peanuts.
the kittens are pushing the peanuts back.
117.
Force on the peanuts from the kittens is negative 117.6 newtons. Now, a quick note. Remember, friction is normal force times the coefficient? In this problem, the coefficient of friction is 0.3. And this is a force of friction, right?
Yes.
What's my normal force? Don't shout it out because there's a sneaky wrong answer. So when you talk about the normal force, you're talking about the force of one object, I've always said supporting another one, but that doesn't really work anymore. We're talking about the contact force from an inanimate surface between the peanuts and the kittens. So my normal force is actually this negative 392. Right? Because if you think of the kittens up here as a surface, they're going to push down with 392 newtons, right?
Yes. Yes.
Follow?
Yeah.
So you could still do 0.3 times negative 392 to get this friction force. Follow?
Oh, that's cool.
Okay? All right, so now we can find our net force and our acceleration. Any problems?
Nope.
All right, so now our net force is 800 minus 11, or 117.6, so what's that going to be? 682.4 newtons. And then the acceleration of the kittens is, peanuts. Now, as a quick note, you guys, notice, and this is kind of what Adam was asking about before, the peanuts are still going to move slower than they would if the kittens weren't there, right?
Yep.
Because the peanuts are pushing back, or the kittens are pushing back. All right, so anyway, when you figure this out, we get an answer of 5.69. All right. So, we only have like 3 more minutes here. Tell me something important about these two results.
They're different.
They're different. Which one's bigger?
Peanuts.
The peanuts, right? Because there wasn't enough force to get the kittens accelerating at that same rate. That's why they slide off the back.
Yep.
Follow?
Yes.
So it's like the peanuts move out from underneath the kittens.
Kittens are still accelerating.
It's here. You guys ready for a really loud noise? Oh wait, no, we can't do it. Oh yes, we can. This will be fun.
Oh, why? Why do you do this?
Because,
Science.
For the sake of example.
right? So if I push slowly, they move together, right?
Yes.
If I push too fast, they fall, right? But if you notice, the stool still moved forward before it fell.
Yes.
Daniel, I'm sorry, you're taking a test and there's a ton of noise here. If you need extra time, we'll talk. Yeah. All right, are we good? All right, so that's pushing. All right, we took, is that 2 full days on this? Okay, so we're a little behind. I'm going to abbreviate my pulling notes a little bit. It's really just more of the same. The only difference is instead of the objects pushing each other, they're pulling each other. But conceptually, it's the exact same idea. All right? So, why don't we make the 5-1 assignment due Friday? So that you've got time to work on it. Tomorrow we'll do the pulling notes, and the 5-2 stuff will be due Monday. All right? Good? Okay. 8:40.